this video, let us learn how to plot the BODE's plot for this given problem. Now, what is the difference between this problem and the problem that we solved in the previous video is I have added one quadratic equation or quadratic pole into the g of s into h of s. Okay, so let us see how the stability can be analyzed when a quadratic pole term is given along with the zero or the pole at the origin or the simple pole or simple zeros, whatever it is given. Okay, so anyway, I just wanted to add a gain here, so let me consider gain of 50 in this particular problem. Okay, now, so the first step which we saw in the previous video, so let me not go step by step explanation what I did in the previous video, which was detailed explanation that was given in the previous video. Now we keep on solving this problem step by step, and we try to solve it as quite soon as possible. So I want students, if you want to practice to do this particular problem, keep a similar graph sheet with you and also a sheet of paper and a pen, so that you can also solve this particular problem along with me. Okay, you can also pause the video and try to be with me, so that if you try to solve along with me, you will be able to understand much better. Okay, now first thing is in the given problem, what we need to identify here is whether the given problem is in standard time constant format or not. So I already told you in the previous video what is standard time constant format. So both in the numerator and denominator, s plus phi is there, right? See, if you see in the numerator we have s plus phi, that should be in the format 1 plus ts. So even in the numerator also the equations should be in the form of 1 plus ts. So what we need to do here is we need to take common of certain terms so that this can be converted into a standard form. So it is 50 into, what I need to take common here is phi. So I'll take phi common. So what will I get here is 1 plus 1 divided by phi into s. Whole thing divided by. So in the denominator, s into, I'll take 2 common. So this becomes 1 plus 1 by 2 into s. And here the quadratic term should be 1 plus t into s plus t into s square. Okay, so it should be like in this format. Okay, so for that what I need to do is, if I need 1 plus, the constant term should be 1, so I need to take 400 common here, so that becomes 1. So 400 is common, which I take, that is into 1 plus 32 by 400 into s, right, plus 1 by 400 into s square. So this is the quadratic term we get when we take 400 common, right? So now we need to take all these constant terms and keep all other terms in a separate way. So what do we get here is, I'll see that I'll take this 50 into phi. So I'll take 50 into phi separately, and then I'll write this 1 plus 0.1 divided by phi is 0.2. 0.2, yes, okay. 1 divided by, so I'll take this 2 into 400 separately. So it is 2 into 400 separately. And then I'll write s into 1 plus 1 by 2 into s. 1 plus 1 by 2 is 0.5. So it is 1 plus 0.5 s multiplied by the quadratic term 1 plus, so if you do 32 by 400, I'll be able to get a 0.08 s, 0.08 s added with s square. So 1 by 400 s square will give you 0.0025 s square. So this is the whole equation. Okay. Okay, now I need to solve this. What do I get? 50 into 5 divided by 2 into 400. So what do I get? So if I solve this in the calculator, so I'll be able to get 50 into 5 divided by 2 into 400. So I'll end up in getting 0.3125. So I'll be able to get 0.3125. So what I'll do is I'll just erase on the upper side, and then I'll try to replace that as 0.3125. I'll take the eraser and then I'll try to remove these terms. So here, so let me write this line. So here it is 0.3125. 3125. So this is the actual standard form of the given equation. Okay, now let us go with magnitude plot method. So it's involved in magnitude plot. So what I need to do is I need to first calculate the corner frequencies. Okay, so omega. So I need to find out what are the corner frequencies. So let us do that now. So the first corner frequency is this 0.2 is time. So 1 divided by 0.2. So you'll be able to get 5 radians per second. Okay. And another corner frequency is this 0.5. So 1 divided by 0.5, you'll be getting 2 radians per second. Now, how to find out the corner frequency when the quadratic term is considered? So it is very important to know this step because this is the extra step which we are able to see in this video. Now, initially you saw that the quadratic term was s square plus 32s plus 400. This was the equation. Initially, the question it is given. Now, if you compare this with second order equation, we all know second order equation is s square plus 2 zeta omega ns plus omega n square. If you compare these two terms, if you see here, we are able to see that omega n square is equal to 400, right? 2 zeta omega n is equal to 32. Okay, so therefore, I'll say omega n square equals 400. So I'll be able to get the frequency omega n equals 20 radians per second. Now, when you have a quadratic term, the corner frequency itself is a natural frequency. Keep that in mind. So the corner frequency and the natural frequency will be one and the same. So therefore, omega c for quadratic equation is actually the natural frequency, which is 20 radians per second. If you see this particular problem, omega c1 is 2 radians per second, omega c2 is 5 radians per second, omega c3 is 20 radians per second, because that is how the values are. Okay. So now what I need to do is I need to list out all the omega values. So omega L, initially we take omega lower value, which is less than 2. So we assume always, which I told you, which is 0.1 radians per second. Whereas omega C1 is 2 radians per second. And omega C2 is 5 radians per second. And omega C3 is 20 radians per second. And finally, we need to take one more term, which is omega H, which is more than 20. So I'll take 50 radians per second. So these are the omega values which we have calculated for this particular problem, corner frequencies. Okay, now let us calculate the magnitude values for these corner frequencies. So always, initially what we do here is, we take at omega equals omega L, which is equal to 0.1 radians per second. We have A equals 20 log to the base 10 K value. K value in our problem is what? 0.3125. So 20 log 0.3125 divided by 0.1. So try to find out the formula value for this, and you see what A for omega L that we get. So 20 log of, so let me take the calculator and try to find out what is 20 into log of 0.3125 divided by 0.1. So I'm able to get A omega L, which is 9.88. dB. So this is the first value of magnitude that we have got, 9.88 dB. Let me go with the next one. At omega equals omega C1, and in this omega C1 is 2 radians per second, and the formula remains to be same what we say, what we have written above, which is A equals 20 log of 0.3125 divided by 2. 2 radians, so divided by 2. So what do we get? If I solve this particular problem in the Calc, I get A omega C1 equals 20 log of 0.3125 divided by 2 will give me minus 16.123. So let me take minus 16.12. So this is the second gain that we get at omega equals omega C1. Now let me take at omega equals omega C2, and if you see what is omega C2, it is 5 radians per second. So 5 radians per second. So now the A formula will change. The formula for A now will be equal to gain formula is slope between omega C1 and omega C2 into log of omega C2 divided by omega C1, whole thing multiplied by, whole thing added with A omega C1. Now I think you realize why we need to write a slope table, right? We did not write the slope table for till now. Okay, so this is the reason. See, we need to substitute slope values here. So that is the reason we need to construct the slope table. Okay, so let us try to find out the slope table. Okay, so the first thing will be term, then corner frequency, then initial slope, and final slope. Okay, initially we know that the term k by j omega, which is 0.3125. So if I substitute s as j omega, I will replace s with j omega. I'll just write it here only. So it is 0.2 j omega divided by point s j omega. So point f j omega. Similarly here, point by j omega. Here 0.08 j omega, and this is j omega square. So j omega, and this is j omega whole square. Okay. So the first term is, so first term will always be 0.3125 divided by j omega. So the corner frequency is, initially we don't have anything, and due to one's pole at the origin we have initial pole is minus 20, whereas final slope we don't have anything initially. Now the second term is the first corner frequency, which is 2 radians per second. Right? This is the first corner frequency, 2 radians per second, and that 2 radians per second is obtained because of which term? It is because of 1 divided by 1 plus 0.5 j omega. So that is what we write here, 1 divided by 1 plus 0.5 j omega. Now this is a simple pole. If you see here, this is a simple pole. So simple pole will give you a slope of minus 20, but the final slope is minus 20 initially for this, and minus 20 the earlier slope. Both gets added up and it becomes minus 40. Minus 40 is the final slope. Now the next corner frequency is 5 radians per second. So I'll write here 5 radians per second. And this 5 radians per second is obtained because of this 0.2. So this is a simple zero. So which is 1 plus 0.2 j omega. So simple zero will offer a slope of plus 20. So the resultant final slope is minus 40 plus 20 will be equal to minus 20. Finally, you have omega C3, which is 20 radians per second, 20 radians per second. And this is because of the quadratic term which we have here, which is 1 divided by 1 plus 0.08 j omega plus 0.0025 j omega whole square. So this is the factor. This is a term which generated on kernel frequency 20 radians per second. As I told you in the previous video, the quadratic pole will offer a slope of minus 40 dB per decade. Will offer a slope of minus 40 dB per decade. So the final slope will be minus 40 added with minus 20 will give you minus 60 dB is the final slope. Anyway, all these values are in dB per decade. dB per decade. Okay. Now we got the slope table. Now, what is the slope between omega C1 and omega C2 is minus 40. This one, first one, minus 40. So therefore, I'll substitute minus 40 here. I'll substitute minus 40 here. So this is equal to minus 40 multiplied by omega C2 is 5 and omega C1 is log of 5 divided by 2 to the base 10, and this gets added with a omega C1. A omega C1 is negative, so this gets subtracted with 16.12. Now let us see what is a omega C2 is. Final value. So let us look into the calculator. It is minus 40 multiplied by log of 5 divided by 2 is minus 15.91, and that gets added with minus 16.12. So you'll be able to get minus 32.03. Minus 32.03 dB is what the gain a omega C2. Now let us go with calculating the gain at omega equals omega C3, and omega C3 value is 20 radians per second. 20 radians per second. So the value of A now will be equal to slope between omega C2 and C3. Well, see, this is omega C1 and C2, so this becomes C2 and C3 multiplied by log of omega C3 divided by omega C2 added with A of omega C2. Now let us see what is slope between omega C2 and C3. The next slope what you have here is minus 20. So therefore it is minus 20 into log of 20 divided by 5 into added with, as it is negative, so this gets subtracted with 32.0. Therefore, if I solve this, minus 20 into log of 20 divided by 5 is minus 12.04, minus 32.03 will give you minus 44. So therefore, A omega C3 is minus 44.07 dB. Finally, at omega equals omega h, which is equal to, so omega h, which I have considered is 50 radians per second. 50 radians per second. So for this, let me take magnitude formula. A equals slope between omega C3 and omega h multiplied by log of omega h divided by omega C3. Always higher value should be at the top and lower should be bottom. So the base 10 plus A of omega C3. So the slope between omega C3 and omega h is this slope, which is minus 60. So therefore, minus 60 multiplied by log of 50 divided by 20 added with, so this is to the base 10, added with, so this is a minus value of omega C3 amplitude, so therefore it is minus 44.07. So this will give me minus 60 into log of 50 divided by 20 is minus 23.87. So minus 44.07 will give you minus 67. So A omega H equals minus 67.94. So now what we got here is the amplitude for individual omega values. Now let us go and plot the magnitude plot in the BODE's plot diagram. Okay. Now let me take the omega values first. Let me teach you the omega values how to take. Like earlier, whatever we did, we start with omega, which is 0.1. So this value is will start with 0.1 radians per second. So this is 0.1 radians per second. Radians per second. As I said you, this increases 10 times. So this becomes 1 radians per second. So in between, this is 0.1, 0.2, 0.3, 0.4 till 1 radians per second. Similarly, this one, once this is 1 radians per second, this becomes 2, 3, 4, 5 till this is 10 radians per second. 10 radians per second. So 20, 30, 40, 50, this is 100 radians per second. So this is 100 radians per second. 200, 300, 400, 500. So this is 1000 radians per second. So finally, this is 2000, 3000, 4000. So this becomes 10,000 radians per second. Fine. So this is how we mark the frequency now. So out of those frequencies, 0.1 is here. So this is 2 radians per second. 2 radians per second. And we have 5 is here. This is 5 radians per second. Similarly, we need 20 radians. So this is 20 radians per second. And if you see this 5, which you see here, this is 50 radians per second. So I just mark the frequencies which we have omega C1, omega C2, for which we need to mark magnitude plot. So now the magnitude values is lower value is 9.88, means the positive value is 9.88 dB. Negative value is going till minus 67.94. So what I do is I will start this as 0 dB line. This as 0 dB. So this point is 0 dB. This is 0 dB point. Now what I do, I'll draw a small line for 0 dB, which is very important. So this is 0 dB line. So this is 0 dB line. 0 dB line. Okay. Now I'll mark the magnitude. So let me take this as 10, this as 20. At the bottom I have minus 10, minus 20, minus 30, minus 40, similarly minus 50, minus 60, minus 70 till here. Okay. Now at omega equals omega C1, omega L 0.1, I have a magnitude of 9.88. So from here to here is 10. So it is 2, 4, 6 and 8. Somewhere here 9.88 is somewhere here. So let me mark that as 9.88. This is 9.88. At 2 radians per second, we have minus 16.12 dB. So at 2 radians per second, we have minus 16 point. So minus 10 is this line, minus 12, minus 14, minus 16.12 is somewhere this point. This point. Similarly, at 5 radians per second, so this is the 5 radians per second, you can see here 5 radians per second. Minus 32.03 dB, so minus 32.0 is somewhere here. So this is minus 32 point. Here, this is minus 30, so minus 32 is this. So 5 radians is this. So this is the point. Okay. Then at 20 radians it is minus 44.0. So 20 radians is this line. This is the line which is 20 radians per second. So in that line, minus 44 is this is minus 42 minus 44 is this point. Then finally at omega is 50 radians per second, we are minus 67.94. So 50 radians per second is this line, if you see at this line. So therefore, this is the line. So therefore, I have minus 67.94. So minus 67.94 is minus 62, minus 64, minus 66, 68. So 67.94 somewhere it will go. Now what I need to do? I need to join these points using a scale. So I'll join these points using a scale. Now first of all, I need to hold here and then come to this point. And so, see, initially in the first stage itself, the 0 dB line is crossed. Okay. Similarly, from here to here. Similarly, from this point to this point. And finally, from this point to this point. Okay. So this is my magnitude plot. Let me write the slopes for everything. So the first slope is, so this is the first line. The first line slope is, if you go back, initial slope is minus 20 dB. So minus 20 dB per decade. And this is the second slope. So the second slope is minus 40 dB per decade. Minus 40 dB per decade. Now there is the third line. The third slope is, if you look back into the table, it is minus 20 dB per decade. Minus 20 dB per decade. Finally, the last line slope is minus 60 dB per decade. Minus 60 dB per decade. So minus 60 dB per decade. Minus 60 dB per decade. So this is all about the magnitude plot for this particular problem. And our 0 dB, the point where the 0 dB line is touching is this point. So let me mark that point. This point, which is exactly 3 radians per second. That is the 0 dB line. 3 radians per second is where the 0 dB line is crossing the magnitude. So anyway, now let us go and, okay students, now let us see how to plot the phase plot for the phase plot. Now to do the phase plot, before finding the final angle equation, we need to generate angle equation, that you all know. So before generating the final angle equation, what we need to do is, we need to take this quadratic equation and find out the value of zeta and omega n. We need to find out what is the value of the zeta and omega n. What is zeta and omega n value? And then finally, why zeta and omega n is required, I will tell you later. So if you take s square plus 32s plus 400, omega n we already calculated earlier. Corner frequency is omega n, which was 20, which we saw earlier. Anyway, we'll do it again. So if we compare this equation with the standard second order equation, which is s square plus 2 zeta omega n s plus omega n square, we can easily say that omega n square is actually 400 equals 400, where omega n is actually equal to 20. So this is the natural frequency omega n. Now if I want to find out zeta, we need to take this, which is 2 zeta omega n, and that is actually equal to 32, right? That is actually equal to 32. Now if I go with zeta value, zeta will be equal to 32 divided by 2 times omega n. So we know omega n is 20, so if I substitute that, I will be getting 32 divided by 2 into 20, so which is 32 by 40. So finally I will be able to get zeta equals 0.8. Zeta is 0.8. So we got zeta 0.8 and omega n, which is 20. Now we take this equation and then try to write it in a standard form. So what do we get here is 50 into 5 plus j omega. So S should be replaced with j omega. divided by j omega into j omega plus 2 into j omega square plus 32 j omega plus 400. Now, when we are writing the angle equation, so the angle for this particular equation, so angle of j omega into h of j omega will be equal to, the angle of 50 is 0 degree, we all know that, because tan inverse of 50, tan inverse of 0 by 50, because imaginary term is 0 and 50, so therefore 0 by 50 is 0, so tan inverse of 0 is 0, and we get angle for 5 plus j omega is tan inverse of omega by 5, and we get the angle for j omega is 90 degree, because tan inverse of omega by 0, anything divided by 0 is infinity, so tan inverse of infinity is 90 degree, and tan inverse of j omega plus 2, so it is omega by 2, into tan inverse of, so the quadratic term equation is very important. So this is the equation, common equation for every quadratic equation that we try to see in the problem. So tan inverse of 2 times zeta into omega by omega n, okay, whole thing divided by 1 minus omega by omega n the whole square. So this is the formula, keep that in mind. If you get any quadratic equation, this is the formula, quadratic pole, this is the formula what we write. And we know that omega n equals 20 and zeta is 0.8. Substituting that, finally the angle equation will be tan inverse of omega by 5, which is 0.2 omega, minus 90 degree. Tan inverse of omega by 2 can be written as minus tan inverse of 0.5 omega, minus tan inverse of 2 into 0.8 is 1.6 into omega by 20, divided by 1 minus omega by 20 the whole square, this whole thing. So this is the angle equation which we need to use for finding the phase plot. This is the angle equation which we use for finding the. Okay, now we have generated this equation for finding the angle to plot the phase. So let us now decide what value of omega will give minus 180 degree. This is what we need to do always when we plot the phase. Okay, so we need to check for what value of omega minus 180 degree will be obtained. So just consider omega equals 17 and check what you get. So let me check. So when I take omega equals 17, I'll be getting tan inverse of 0.2 into 17 minus 90 minus tan inverse of 0.5 into 17 minus tan inverse of 1.6 into 1.6 into 17 by 20, and this whole thing divided by 1 minus 17 divided by 20 whole square, and then close the bracket. And this will give me, if you see, for 17, I am getting the angle which is minus 178.14. I think a little bit of more of 17. So let me go with 17.5. And the angle what I get, let me check. For 17.5, the angle is, for 17.5, the angle what I am getting here is minus 180. So therefore, the omega value what we get minus 180 is for 17.5. So therefore, the omega value is 17.5, for which we are able to get minus 180 degree. Okay. Now what we do, we will try to find out what is the value for 2, what is the value for 5, then 10, then 12, then 15, and then let me go with 19, 20, 30, 50. So these are the angles which we are going to now calculate for these values of omega. So these are the angle values that we got for different values of omega. And at 17.5, we are able to get minus 180, 179.9, minus 180 degree. Okay. So as per the angle equation we have generated, so these are the angle values that we have got. Now we are going to plot these angles in the BODE'S plot, where the magnitude plot is already been presented. So see the angle variations from minus 122 to minus 33.16 for 30, omega value 30. So therefore, what I'll do is I will be taking minus 180 somewhere here. So if I take this as minus 180, and I'll be taking this as minus 160, minus 140, and this will be minus 120, minus 120, and this will be minus 100 degree. Now I'll draw, as usual, I'll draw a line for minus 180 degree. A straight line should be drawn. So I'm going to draw a line for minus 180 degree. So this is minus 180 degree line. So this will be 200, and this will be minus 220, and this will be minus 240. Now let me go with omega value. So at omega equals 2, we got minus 122.37. So minus 122.37 is somewhere here, and we need to mark it at 2 radians per second. So let me check where is 2. This is 2 radians per second. See this line. This line is 2 radians per second. So this, I'll just put a reference there. So that line is 2 radians per second. Now I need to mark it for minus 122.37 at 2 radians. So this is minus 122.37 will be somewhere here. Okay. So somewhere at this point is minus 122.37. Now let me go to the next value of omega. At omega equals 5, I got minus 136.30. So omega equals 5 is somewhere this line. So this is my omega equals 5 line. So this line. So minus 136.30, minus 136. So here minus 120, 122, 124, 120. Okay, 20 division, 20 divided by 5 is 4. So 124. I'm sorry, I think 120. First line, the first one will not be here, because the first value is 122.37. So every division is of 4 units. So therefore, at 2 radians per second, 122 will be between 120 and 124. So I think it will come here somewhere at this point. So somewhere it comes at this point. Okay, sorry. It comes somewhere at this particular point. Now coming to 136 point, well, actually at 5 it is 136.30, minus 136.30. So it is 124, 128, 132, 136. So 136 for 5 radians per second. So 5 radians per second line is this one. So this line. So this is 5 radians per second. So 136 is somewhere this one. Okay, this point. This point. So that is for 5 radians per second. Now let me go with next angle. The next angle is minus 152.10 for 10 radians per second. Where is 10 radians per second? So this is 10 radians per second. Minus 152.10. Minus 152.10. This is 10 radians. Minus 152. So 144, 148, 152.40. So this is 10 radians. So somewhere I'll be putting point here. 152. So 144, 148, 152, somewhere here. So the point will come here. Okay. Now coming to next angle. Next angle is at 12 radians per second, which is minus 159.46. Minus 159.46 at 12 radians per second. So 12 So this is 5, 10, 11, 12. So this second line is 12 radians. So the second line is 12 radians and it says 1 near to 160. So somewhere it comes here, right? So at 12 radians per second, it is minus 159.46. So minus 159.46 somewhere comes here. And then I do have at 15, which is minus 170.80. So what angle it is? 15 minus 170.80. 15 is fifth line from here. So this is 15. So 170 is 164, 168, 170 points somewhere here. So this is the point. So this is the point. Somewhere here the point will come. Okay. Similarly, we do have at 16 minus 174.52. So 174.52 at 16. So this is 16. So 174.52. So this is 174. Then I have my 17.5 minus 180. So 17.5 is, so this is before 3 scale. So where is 20? This line is 20. So 20, 19, 18, 17.5. So somewhere at this point is my, this is 180. So I'll make it in a different color because that point is very important, minus 180. So this is minus 180. After that, I do have for 19 minus 185. For 19 is something is this. So 19 is somewhere at this point. So this is 19, 183. Okay. But we started from 2 radians per second, but unfortunately you see here, the 0 dB line is here, 0 dB point is here. So we need to take the value of angle even at 0.1, 2, 3, 4, and so on. Okay, we started from 2 radians per second, but we need to take omega value for 0.1, 0.2 till 1 radians per second. So here, if you're able to see these points that we got for an angle, phase angle, but unfortunately we have a 0 dB point at this angle, at this particular stage, because at 0.3 radians per second. Therefore, what we need to do is we need to make sure the phase plot is taken for this range also, so that the phase plot will start from here. So what I'll do is I'll try to calculate the phase plot for even 0.1 omega values and all. I've done that. If you see that for omega 0.1, I'm able to get minus 92.175. So therefore, I'll mark that minus 92.175. So here minus 80, minus 84, minus 88, minus 92. So this is the point minus 92. So somewhere the point will come here. Okay, so the point will come here for 92. This is the point 92 degree for 0.1 omega. So if I go with the next value of omega, which is 0.3, it is minus 96.47. So where exactly minus 96 comes? 96 point is this. So this is 96 for 0.3. So I'll take 0.3, which is 96 here. Little bit more of point. Okay. Now then what I did is I had taken for 0.4, which is minus 98.56. Minus 98.56 scale is very near to 100, which is for 0.4, and 0.4 is this. Very near to 100. And then I took for 1 radians per second, I got minus 109.8. So 109.8 is minus 100, minus 104, minus 108. So the second line. So this is the point which is for 1 radians, because this is 1 radians per second. So therefore, I got a point which is 1 radians per second. I got somewhere around 109 point something. Okay. Anyway, now what I'll do, I'll join these points to make the phase plot. To make the phase plot, I'm going to join this point. So from here, I'm going to join this point, from here to this point, from here to this point, and then from here to this, and then from here to this point, and then I'm going to join from here to this point, and then from to this, then from here to this to this point and this point. Okay, fine. So this is what we have got. Now what we'll do is we'll try to draw a vertical line for a 0 dB point and a vertical line for minus 180 degree point. Okay, so this is 0 dB, where a vertical line and a vertical line which crosses the phase plot. It should cross the phase plot minus 180 degree like this. Okay. Similarly, I'll go with minus 180 degree line and try to plot a vertical line for that. So this is minus 180 degree. I will draw a vertical line straightly like this. It will go further and it should also cross the frequency. Okay, fine. So I hope you got it. Now this is 0 dB line. Now the phase margin is, what we have got here is from here till here is your phase margin, and the gain margin what we have got here is from here till here is our gain margin. So precisely if you calculate, the gain margin is touching minus 42, 43. So 43, as it is below 0 dB line, therefore gain margin is plus 43 dB. And if you look into the phase margin, angle you have to look, it is starting from minus 84, 88, 92, 96. So it is starting from 96 and ending at 180. If you see the difference between 180 and 96, so 180 minus 96, 180 minus 96 is 84 degree. So phase margin is 84. As it is above minus 180 degree line, so this is also positive, plus 84 degree. Both are positive, and meanwhile you have omega, the gain crossover frequency omega Cp, which is equal to 0.3 radians per second, and the phase, so this is your gain crossover frequency, and this is phase crossover frequency omega Cg, which is equal to, so this is 10, 11, 12, 13, 14, 15, 16, somewhere around 17 radians per second. But anyway, it should be exactly 17.5, because at 17.5 we got minus 180 degree. So that is very important. Okay. So therefore, as you see, both phase margin and gain margin both are positive. The system is stable. Okay. I hope you understood the BODE's plot with this video and also the previous video. I have covered two different examples, and watch this video again and again if you don't understand. I hope you will be able to solve it. Okay, you will be able to understand the BODE's plot, and you will be able to do any other problem if it is given to you. Thank you.